We're back. After 3 weeks off, I am energized and bursting to share this material with you. Thanks for sticking with us during the breaks.
Great to be back.
We are returning with what might be the single most ambitious deep dive we've ever attempted.
I'd agree with that.
Because, honestly, the sources you all compiled for this synthesis, they're just spectacular.
It's an intellectual Everest, truly. The core thesis, and it draws really heavily from this material titled The Circle That Built Intelligence. It treats basic geometry not as some isolated topic, but as this central organizing principle for arithmetic, analysis, and ultimately artificial intelligence.
It really does feel like a mathematical Rosetta Stone, like you said.
Exactly, a Rosetta Stone. Fantastic stuff.
What's our mission statement for the next 30 minutes, given how broad this material is?
It's simple, but vast. We start with high school math. Literally circles and trig.
Okay.
And we end up deep inside the inner workings of an AI model like GPT-4. We're going to touch on Galois theory, Chebyshev polynomials, the Langlands program, nilpotent elements.
Philosophical take on zero.
That's a list.
This deep dive is about proving that symmetry isn't just pretty, it's profoundly generative. It is arguably the core algorithm of reality.
Okay.
Strap in.
Seriously, buckle up. We are diving immediately into a problem that, look, every student of trigonometry probably encounters, but almost nobody realizes the incredible mystery hidden inside it. Okay, let's unpack this setup. Picture it, a perfect unit circle at the origin of a graph.
Standard stuff. Now we're going to place 77 dots evenly around it. Think numbers on a clock face. We start numbering at $, not 0, and go up to 6. 6 points we're interested in for now.
Excluding the point at 3 o'clock, $, for the moment. We're primarily interested in the horizontal position of these dots, the x-coordinate.
Okay, coordinate.
So we take the cosine of the angle for each dot, but, this is important for later, we scale that cosine value by 2.
Times 2.
It connects it to the Chebyshev polynomials we'll get into. So for our 6 dots, $2 through $6, the positions are 6K, $2, 2T7U.
I really want you to picture these ugly, seriously. We're dealing with cosines of angles like 2 pi over 7, 4 pi over 7. These aren't nice angles like 30 or 45 degrees.
Not at all.
$6 is about 1.247. 6 by 2 is about minus 0.445. Then 6 by 3, roughly minus 1.802.
Yeah, they involve complex algebraic expressions. You'd expect nested square roots, maybe cube roots. They look irrational.
They look like total algebraic chaos. Just a mess of numbers.
So imagine you're given these 6 messy, seemingly random real numbers. Someone asks you to build a polynomial using these numbers as the roots.
Yeah.
You know, the polynomial 7x equals x by 1, x by 2, all the way to 10 I $6.
Multiplying 6 factors together, each with one of these messy numbers.
Expect the coefficients of the final polynomial to look like.
Oh, just as messy, right. You'd expect the coefficients to be full of square roots of 7, maybe nested roots, maybe even some pi stuff from the cosines. Utterly irrational.
That's the rational expectation.
Right.
Here's the genuine, mathematically guaranteed shock.
Okay.
When you perform that polynomial multiplication, multiplying out all those terms involving those 6 chaotic, irrational-looking roots,
Yeah.
the coefficients simplify perfectly. They just clean up. The resulting polynomial is built exclusively out of perfectly clean whole numbers, integers.
No way.
We can show you the concrete example for one $100. When you do the multiplication, you get 7x plus 2, 5, 3x4, 6x3, 2x2 plus 4x plus 1.
Okay, hang on. Look at those coefficients. 1, 2, minus 3, minus 6, 2, 4, 1.
Just simple integers.
Does it make
It's
sense?
an immaculate structure.
Yeah.
How does that happen? How does it arise from what looked like transcendental messiness?
This isn't just a fluke for one epsilon of the Euler. This phenomenon holds true for any number of dots. You always get integer coefficients for this polynomial of f of x.
So the starting point, the roots, 6 color, look complex and irrational. But the final state, the polynomial built from them, is perfectly rational and integral.
Okay, so this is the core mystery we're setting up. Why does the simple act of putting dots on a circle and looking at their horizontal projections create a system where multiplying those messy, irrational numbers is guaranteed to produce clean integers?
This is where math stops being just calculation and becomes about, well, profound structural symmetry.
The answer lies in the deep arithmetic structure these numbers belong to.
It's all about the field they live in.
Let's transition. Why is the system guaranteed to have this integer structure? Walk us through it.
Think of it like citizenship. The 6 gold values aren't just random real numbers. They are highly structured algebraic entities. Specifically, they're called algebraic integers.
Algebraic integers.
They belong to a special number field, the cyclotomic field, usually written as Galois math BBQ.
All right, let's ground the tank for the listener. What is that symbol? It sounds important.
It is the fundamental building block, the primitive noth root of unity. In complex numbers, it's raised to the power 2.
The complex number that if you multiply it by itself all our times, you get back to 1. It's like the fundamental point on the unit circle in the complex plane for division.
Exactly. The 6k values we started with are derived directly from these complex roots using Euler's formula. It equals 2 punks, 2 punts, tankano, comb. That's the same as the tank plus the tank.
6 Heller is the sum of a complex root, and it's a complex conjugate. That ties them together very tightly.
Precisely. They are inherently linked by complex conjugation and addition. They share a deep algebraic kinship.
Okay, I see the kinship. But how does that family relationship force the polynomial coefficients, multiplying and adding these 6 cells, to become simple integers? That's the core leap, right?
This is the genius of Galois theory. The cyclotomic field EQ2 isn't just a set of numbers. It has a structure group. This is the Galois group, written Galois Gunner.
A group, like a set of operations.
It consists of automorphisms, which are structure-preserving maps or symmetries of the field, ways to shuffle elements without breaking arithmetic rules. Addition, multiplication.
Okay, symmetries of the field.
These automorphisms do sigma must leave the rational numbers untouched. They only shuffle the new numbers introduced by Zekta.
What happens when we apply one of these symmetry operations, sigma, to our fundamental building block, dollars?
Sigma has to map to another primitive root of unity. So it shuffles the primitive roots of unity. It takes Zekta and maps it to some number co-prime to the nulls.
It swaps one generator for another.
Yes. Since our root $6 are defined purely in terms of sectan as zetank plus zektan, what does the action of sigma do to the whole set of roots?
But if sigma shuffles the tanks, it must shuffle the 6 too. It swaps them.
Exactly. The Galois group doesn't change the set of roots. It merely rearranges them.
Let me make sure I grasp this. The symmetry operations of the field, the group actions, take the list of our roots and reorder the list.
That's the principle of Galois invariance in action. The set as a whole is stable under the group. Now think about the polynomial f and xtain. It's defined by these roots, its coefficients. How were they calculated from the roots?
The constant term is the product of all the roots. The coefficient of 6 is the sum of all roots. The next one is the sum of products of pairs of roots.
They are the elementary symmetric polynomials of the roots. They treat all the roots symmetrically.
Symmetric polynomials. If the Galois group shuffles the roots around, but the polynomials are symmetric.
What happens to the value of the symmetric polynomial when you shuffle its input?
By definition of symmetric.
So the coefficients of Fibonacci being symmetric polynomials in the roots must remain unchanged, invariant under the action of every automorphism sigma in the Galois group.
What does that tell us?
Galois theory tells us something profound. If a number within the field extension is fixed by every automorphism in the Galois group, that number cannot be one of the new complicated numbers. It must belong to the base field.
It must be rational. It must be in math.
That's the guarantee of rationality. The symmetry forces the coefficients back into rational numbers.
Okay, that explains why they aren't irrational messes. Why integers? Why not, say, 12 or 34?
There's a theorem in algebraic number theory that says if the roots of a monic polynomial are all algebraic integers, and the coefficients are rational numbers, those coefficients must be rational integers. They have to be in math Binet.
The algebraic integer nature of the roots upgrades the rationality of the coefficients to integrality.
The integers aren't accidental. They are a necessary, inevitable consequence of the system's perfectly balanced symmetry.
That is beautiful. Each irrational root brings its algebraic conjugate friend to the party, as the source material put it.
That's a great analogy.
When you calculate these symmetric things like the sum or the product, the weird irrational parts of each number just perfectly cancel each other out.
That's the intuition. Symmetry forces cancellation.
Amazing. You mentioned the symmetry goes deeper, giving us an explicit formula using Chebyshev polynomials.
Chebyshev polynomials, the master key, and for good reason.
Why are these polynomials the natural harmonics of the circle? And how do they directly explain our integer polynomial phenix?
Chebyshev polynomials, first kind, Tx, are defined by a unique property.
Cos theta.
They relate the cosine of an angle to the cosine of that angle.
Exactly. They are the only polynomials that do this. So they are perfectly designed to articulate the harmonic structure of the circle using polynomial tools like recurrence relations. They form a stable orthogonal basis for functions defined on the interval -1, 1, which is exactly the range of cosine.
And our roots, $2 facts, were $2 signs, so scaled cosines.
Correct. Now consider the polynomial equation Tmx equals where $6 equals $2, which is $1.
The secosine equals interior, which is $.
That happens when a show is a multiple of $2, so theta exposes $2 for integer color.
The solutions to TNX showed exactly 6k values, but for all k's from 1 to 1.
Ah, so it includes the $k point, $6 because $2, which we excluded earlier to get Phoenix.
The polynomial Taylor-Liners has no roots, including x2 to tiers. Our desired polynomial families has only the roots k landed to 1x. How do we get Phoenix at x from sen x apart?
We divide out the factor corresponding to the root sextuplets. We divide by 1.
So basically, that leads directly to the clean formula. Phoenix dollars is proportional to TNXL. There's a factor of 2 usually included.
Phoenix is 2n, x2, 1, x2. Wow. And because Chebyshev polynomials have integer coefficients and follow nice recurrence relations,
this formula instantly transforms the problem. Instead of multiplying messy irrational numbers, we're doing a structured polynomial division involving well-behaved Chebyshev polynomials. The integer coefficients of Pfennig-Astors are essentially guaranteed by the recursive integer structure of TNX.
abstract algebraic fields and the analytic structure of harmonics, like Chebyshev polynomials on the other, that feels like a really profound unity.
It absolutely is. And understanding this unity, this connection, is the key that's going to unlock our understanding of how AI works.
Symmetry explains the integer coefficients, local properties of the polynomial. The harmonic symmetry of the circle also leads to some striking global invariants, properties describing the whole system at once.
That's right. The source highlighted 2 really beautiful ones. The first is a multiplicative invariant. It feels a bit like calculating the determinant of a matrix. We look at the product of a slightly different but related set of values.
Yeah.
Take the product 2 cross 1 and 2.
So the product of 2k for all original roots, 6k's. What happens when you multiply those 6 and non-ional irrational terms together?
The result is astonishingly clean, perfect square.
2 and lambda squared, just the number of dots squared.
Yep. For our 1 ends to 97 case, you multiply those 6 random positive numbers together, and the product is exactly $72.
Wow. Think about the improbability of that 6 numbers multiplying to exactly 49.
It's a foundational result in algebraic number theory. It's linked to the discriminant of the cyclotomic number field. It measures the size or ramification of the field.
Okay, a multiplicative invariant to 2 algebras. What was the second one? You said additive?
Yes, this one feels more like a trace. We sum the reciprocals 2 multiplied by 2 for all the roots.
Adding up the inverses of those numbers, what does that come out to?
Again, a perfectly clean rational number. 2
Use 12, always. For 127, this sum is 72 $1 1 nonce. 12 equals 48, 12 2, which is exactly 4.
Adding 6 complicated reciprocals gives 4.
It's another signature of this incredibly high underlying symmetry. These results connect us directly to the analytic side of mathematics.
This sum is related to the expansion of the cotangent function around 0, and it connects to special values of the zeta function.
Okay, we don't need to dive into cotangents and zeta functions right now.
No, but you need to appreciate this sum of reciprocals acts as a bridge connecting basic circle geometry to deep global analytic functions in mathematics.
Got it. Irrationality cancels itself out via field symmetry to produce integers.
Great way to put it.
Where else do we see this exact mechanism at play? The sources pointed us straight towards the Fibonacci sequence.
Yes, and this shows the deep unity we had to emphasize. The Fibonacci numbers, 1, 1, 2, 3, 5, 8, they're integers.
Right.
But how are they often calculated, especially for large Nuller dollars, using Binet's formula? That formula is full of irrationality.
Binet's formula is 1 and fracn and frac barfin.
It's exactly. Where Varphi is the golden ratio, $1 plus 2, and Varphi is its algebraic conjugate, $1 stopin, both irrational, involving square.
Every time you calculate a Fibonacci number using this formula, you're taking powers of these 2 irrational numbers, subtracting them, and then dividing.
Yep. Miraculously, the squared in the denominator must perfectly cancel out the irrationality from Varphin and Barphin in the numerator, leaving you with a perfect integer Fibonacci every time.
How does that cancellation happen? Same mechanism?
It's the same mechanism. The golden ratio of Varphi is a root of the simple quadratic equation 6 by 2 by 1 equals a Zoller. The other root is Varphi.
Okay.
These two numbers, Varphi and Varphi, are Galois conjugates in the quadratic number field Math BBQ, just like Satankandoka conjugates in the cyclotomic field.
The structure of the field Math BBQ has a symmetry swapping squart-dick with squart the Varphi. It swaps Varphi and Varphi.
Exactly. Binet's formula is symmetric with respect to this conjugation, up to a fine change that cancels with the squared denominator. The symmetry forces the result to be rational, and since Varphi and Barphi are algebraic integers, the result must be an integer.
Wow. The squarter plays a role analogous to the Noth roots of unity. It defines the field extension and provides the necessary symmetry to turn apparent chaos into perfect integer order.
That's the key insight. We're looking at two different types of field extensions. Cyclotomic fields built from roots of unity, and quadratic fields from square roots. But the fundamental principle of symmetry-induced integer generation is identical. Irrationality plus symmetry integers.
Does this generalize if we use other square roots instead of squared?
It does generalize beautifully, connecting to deeper number theory. If you replace scored with scorebot, where parf is a prime number congruent to 1 modulo 4, like 5, 13, 17, you can define analogous integer sequences using the same mechanism.
Primes congruent to 1 mod 4. Isn't that related to sums of two squares?
Two squares theorem states that primes p equivalent mod 4 are precisely the primes that can be written as the sum of two squares. This ability is deeply tied to how the prime behaves in quadratic fields, like math BBQ.
So this ties our simple circle problem through the Fibonacci example into classical number theory, like Fernet's theorems.
Yes, into the broader framework of class field theory, which studies the relationship between number fields and their Galois groups, explaining these kinds of connections between the arithmetic properties of different fields. It's all proving that the structure guaranteeing integers in the circle problem is the same structure, ensuring Fibonacci numbers are whole. It's a universal principle.
Let's introduce a different element, prime numbers. We think of primes as points of perfect order in the chaos of integers.
The fundamental building blocks.
Sources describe them as spectral scramblers on our perfect circle. How can primes create chaos?
It's fascinating. Consider a simple, deterministic map on the circle, represented as the interval 0 to 1. You take $0.6, multiply it by a prime number, and take the fractional parts.
Multiply by POS, wrap around the circle.
If you start with almost any irrational point, $6 in the circle, and you just keep applying this map, the sequence of points looks completely random.
Random, but a deterministic formula.
Statistically, the sequence passes most standard tests. It looks like you're just scattering points randomly onto the circle.
So primes act like DJs of arithmetic, as the source said, remixing the nice harmonic modes of the circle into something that looks like noise.
That's a perfect analogy. This process generates convincing pseudorandomness, and the prime part is crucial. If the multipliers were composite, say 6, the sequence would eventually fall into short, predictable cycles.
Why?
Because multiplying by 6 mod 1 doesn't mix things as thoroughly. But because B-Dolar's prime, it ensures that the orbit of the point doesn't get trapped easily. Over time, the sequence becomes distributed around the circle.
Equidistributed, meaning it visits every arc of the circle equally in the long run.
Precisely. Prime scrambling leads to a uniform covering of the circle. It's a deterministic process generating effective chaos and uniformity.
Okay, that's the dynamics on the circle. How do we link this physical scrambling back to the abstract algebra we were doing with our cyclotomic field math BB2?
We connect it through a key concept in algebraic number theory, the Frobenius automorphism.
Okay.
The Frobenius automorphism map via is the arithmetic version of that spectral scrambling map. 6 docs, masterable px pmod along 1. How does it act on our field elements? How does it act on the roots of unity as ecopon? It acts by raising them to the p-han.
The algebraic symmetry operation associated with the prime dollars is literally raise the fundamental root to the power Baller. That's the direct algebraic counterpart to multiplying the position by ballers on the circle.
The prime number power itself is now acting as an element, or generating an element, of the Galois group math BQ. It's shuffling the roots of our polynomial according to this pale power rule.
Prime scramble points on the circle is mirrored by how they scramble roots algebraically.
Perfectly mirrored.
Yeah.
And this leads to prime splitting. When we consider a rational prime 2, 3, 5, 7, and look at it inside the larger number field, does it stay prime or factor into multiple prime ideals within that bigger field?
Does it break or stay whole?
The pattern of splitting is governed by the relationship between poly and dollars, specifically the order of p in dollars. Let's call this order 4. It's the smallest positive integer 4, such that p of f1 p mod 2 null.
The order of p mod nullers. Let's use our one-dilateral example again. What happens if the prime p of nuller comes into the field?
Okay, we need the order of $100 would modulus $11 equip 4 p mod $7. That's not 1. Oh, wait, $11 equip 4 p mod $7. Is that right? No, $11 equip 4 p mod $7. Ah, the example in the outline used primes co-prime to 7. Oh, wait, the outline did use 11. Let's check $11 p mod 7DL. $113 equip 4 times 2, 8 equip 1 equip 4, 7. $112 equip 42. 16 equip 4, 2. $113 equip 4 times 2 equals 8 equip 1 p mod $7. The order for 3, not 1. Okay.
The outline said order 1 split completely. Maybe the example was meant for primes in the ring of integers, not rational primes. Let's look at the example primes given 2, 3, 11, 13, and equiv 3 times 2 times 2, 33 times 2, and 6 equiv 3 times, $34 equiv 3 times 3 times 3 times 1m, $34 equiv 4 times 3 times 3 times 4, 3 times 5, there's 15 equiv 1 p mod 7m.
The ordered phi dollars is 6. That's the maximum possible order since the group size is 732. Since FDSX6 is the maximum possible, the prime 3 remains inert in BBQ. It stays as one prime ideal in the ring of integers of the field.
And how does that relate to the Frobenius map?
Because 2 6c's, the Frobenius map sigma 3, 3, which raises Z07 to the power 3, turns out to be a generator for the entire Galois group. It's a maximal shuffler. It cycles through all 6 primitive roots.
A prime staying inert algebraically corresponds to its Frobenius map being a maximal scrambler.
Consider a prime 2p 2 sigs, order of $2, p-mid 7 and 3, 23, course 1 and 3, it's equal to 1 and 1 years, 1 of fixed 3 2 6.
Okay, for MP3, what does that mean splitting?
The general rule is the prime piece splits into the xi phi factors in the larger field. 1 for a phi for 2 dia 3, we get d dollars at 63. The prime 2 splits into 2 distinct prime factors in math BBQ.
Less splitting than complete, but more than inert, corresponds to intermediate scrambling.
Precisely. The prime number's dynamic behavior on the circle, how much it mixes things, translates directly to its algebraic splitting behavior in the field.
This brings us to one of the most abstract concepts in the sources, but one that sounds evocative: the Gerbe. You said it relates to global consistency.
Yeah, this is deep stuff from arithmetic geometry. The idea is you have all this local information, how each prime behaves, how it splits, how its map shovels the roots in its own world.
Okay, local pictures from each prime.
Sometimes these local pictures, local shuffling rules, don't mesh perfectly. You can't always glue them together smoothly to form a single, consistent global structure.
Like trying to make a flat map of the round Earth, you get distortions where patches meet.
That's an excellent analogy. The Gerbe is a mathematical object that precisely measures this failure to glue smoothly. It quantifies the twist or obstruction to achieving global consistency from local pieces.
It tells you the arithmetic structure of the field might be twisted.
Exactly. It reveals that you can't just add up the local behaviors at each prime and expect to get the complete picture. There's an inherent intertwining between the local structures that the Gerbe captures. Even in number theory, perfect global coherence isn't always guaranteed. There can be subtle obstructions.
This has been an incredible journey through number theory, symmetry, primes. But we promised to connect it all to artificial intelligence.
Right, big payoff.
We established the circle's geometry through harmonic symmetry, integers, Fibonacci, prime behavior. Now, the biggest leap: how does this geometric structure run the world's best AI models, like ChatGPT and others?
We need to talk about the transformer architecture, the foundation of modern large language models. And the absolute core of the transformer, the thing that makes it work so well, is the self-attention mechanism.
Self-attention. Okay.
You can think of attention as enabling auto-contextualization. For every word or token in a sentence, the attention mechanism dynamically figures out how relevant every other token in the sentence or even the whole document is to understanding this specific token.
It learns relationships, which words modify which pronoun refers to which noun, even across long distances in the text.
It does this by repositioning each token in a high-dimensional space. You could call it a context poly based on its relationships with other tokens. The geometry of this space encodes the meaning derived from context.
But wait, a sentence has an order. The dog chased the cat is different from the cat chased the dog. If the attention mechanism is just calculating similarity between tokens, maybe using dot products in high-dimensional space, how does the model know which token came first? How does it handle sequence order?
That is the crucial problem for sequence models. If you treat the input as a bag of words, you lose sequential information. The solution the transformer uses is positional embeddings.
Positional embeddings, I've heard of those. How'd they work?
They are constructed using sine and cosine functions. For a token at a given position, its positional embedding vector has components calculated like 10,000 indexes the dimensions of the embedding.
Okay. Sines and cosines of the position at different frequencies determined by the dimension. Why sine and cosine? Why not just add the position number 1, 2, 3 to the token embedding?
People tried that. It doesn't work nearly as well. The magic of sine and cosine here is their geometric properties, specifically how they handle relative positions, because of trigonometric identities. The sine and cosine embedding for position post plus k can be expressed as a linear transformation, a matrix multiplication, of the embedding for position. This means the relative position is encoded in a way that the attention mechanism can easily learn and use regardless of the absolute positions.
Ah, so the distance between tokens is encoded in a consistent way.
It uses properties of rotation. Think of each pair of dimensions as encoding the position as a point on a circle, rotating at a specific frequency. The attention mechanism, when it computes dot products between query and key vectors, which include these positional embeddings, can measure the phase difference or relative angle between tokens.
The model doesn't have to learn relative positions from scratch. Harmonic encoding gives it that information directly. Positions are points on circles. Different frequencies capture relationships at different scales.
It allows attention to capture relationships from adjacent words, high frequency, to words far apart in the sequence, low frequency, simultaneously and efficiently.
The attention kernel itself, that formula, attention Q kitty V text softmax, it's operating on these harmonically encoded positions. So it's
It's performing an adaptive, learned harmonic analysis on the input sequence. It's like a sophisticated, data-driven Fourier transform that figures out which frequencies or patterns between tokens are important for the task.
So every layer of the transformer is refining this harmonic representation, filtering and transforming information based fundamentally on this circular geometry baked into the positional embeddings.
That's the core idea. But deep transformers with many layers suffer from oversmoothing.
Oversmoothing sounds bad, like blurring an image.
Exactly like blurring an image or losing high notes in music. As information passes through dozens, even hundreds of attention layers, representations of different tokens become more and more similar, average out.
The model loses the fine-grained details, the sharp distinctions between tokens that it needs for complex understanding.
Precisely. High-frequency information, the subtle differences, gets lost. The signal gets smoothed out, damaging performance on tasks requiring precision.
How do we fight oversmoothing? Where does our circle math come back in?
This is where our cyclotomic structure of polynomials provides the salvation. It was demonstrated empirically in a paper by Kim and others in 2023.
Cheat attention.
The cheat paper proposed replacing parts of standard self-attention with an expansion based on Chebyshev polynomials. TK was related to the attention matrix.
Why would a concept from 19th century number theory and approximation theory solve a cutting-edge 21st century AI problem like oversmoothing?
Because it's the same underlying mathematical guarantee. The attention matrix acts like an operator on the sequence, mixing information between tokens. In spectral graph theory, which analyzes such mixing operations, it's well known that using polynomials is often the mathematically optimal way to approximate functions of matrices.
Optimal, because they are the stable orthogonal harmonic basis of the circle.
They're designed for efficient recursion, they remain bounded, don't explode, and provide accurate approximations across the entire spectrum of the operator.
Just like Chebyshev polynomials helped guarantee integer coefficients and spectral stability in our original cyclotomic polynomial 5x's,
Cheat uses the properties of TK to ensure spectral stability in the attention mechanism. It prevents the eigenvalues of the transformation from collapsing towards 0 or 1, which is the mathematical root of oversmoothing. It preserves the high-frequency information by using this naturally stable harmonic basis.
that is genuinely mind-blowing. It's the practical proof of the connection we've been building. The most sophisticated learning mechanism in AI, self-attention, is made stable and effective by borrowing the exact same orthogonal harmonic basis Chebyshev polynomials that stabilizes the arithmetic structure of the cyclotomic field.
The LLM is performing harmonic analysis on a framework deeply related to cyclotomic fields.
The circular geometry we started with in Section 1, it's literally the architectural blueprint ensuring the stability and effectiveness of computational intelligence.
Wow, okay, we need to slow down. We've gone from circles to AI via heavy math. Let's pull back and examine the most fundamental concept that ties geometry to algebra and everything else. Number 0.
A profound.
The symbol of 0 is a circle, but it's more. Sources talk about its conceptual power, the power of nullity, of absence.
0 embodies the discrete continuous duality that's run through this discussion.
In the discrete world, it's the additive identity. 6 is called Orgenkreis. It's the absorbing element for multiplication. 6 times 0 bizor. It represents a boundary, a separation.
Right.
But in the continuous world, 0 is the generator. A zero-dimensional point generates a one-dimensional line, which generates a plane. It's the origin, the seat of intervals, the foundation of calculus, through limits approaching 0. It bridges discrete counting and continuous space.
And the paradox, the really deep idea here, seems to be that absence is often the necessary condition for presence, for structure.
This is illustrated perfectly by our original circle construction. Remember the beginning. We placed 77 dots.
Yes.
And we calculated the polynomial 77 Noxer using root 6k equals 2 for KO lines for KO1 through $6. We left out the root $6.0022. Why did we exclude it? Including it would have changed the polynomial entirely.
What polynomial would we have gotten if we included 6 tanometer 2?
We would have gotten the polynomial related to t and x, including the roots of 2 tiles would mean the overall structure, while still related, wouldn't have the same minimal integer properties. The specific non-trivial stable integer structure depended on excluding that one root.
The structural paradox is crystal clear. The absence of the k-dollar point, the missing root second t2 tons, creates the presence of this specific, interesting, stable, integer arithmetic structure, fun at x stuff.
The missing 0 generates the stability and non-triviality we focused on.
That's a powerful philosophical point, and it extends into the engine of modern computation through nilpotent elements. Infinitesimally zero.
Yes, potent elements. Fascinating algebraic objects.
Yeah.
Think about the dual numbers, often written this is like the real numbers, but you add a new element.
Okay.
And this element has a special property. The itself is not 0, but 2 tiles is not 0.
How can something square to 0 if it's not 0? That breaks the rules of numbers.
It breaks the rules of real or complex numbers, yes. But we can define algebraic structures where it's valid. Think of Aries as an infinitesimal step or direction. A step so small that taking 2 such steps gets you nowhere, 0. But the step itself represents a meaningful non-zero direction or displacement.
Okay. That's abstract.
Right.
Why would mathematicians or computer scientists invent such a weird number? What's it good for?
Incredibly useful. This algebra forms the basis for automatic differentiation.
Automatic differentiation, how computers calculate derivatives, like in training neural networks.
Exactly, without slow, approximate finite differences. Here's how it works. If you have a function and evaluate it not just at a real number, but the dual number a plus b, where b brawlers is another real number.
Yeah.
The result comes out, using just the algebra rule 2f to ft dollars as fa plus b fa.
Whoa.
Look at that. The original function value pops out, plus the derivative phi appears automatically right there next to the nilpotent element air. Yes, the nilpotent element dalim acts like a tag that automatically accumulates derivative information as you compute the function. It carries the continuous structure, the instantaneous rate of change, the derivative within the purely discrete algebraic computation.
That's ingenious.
Geometrically, in scheme theory, this corresponds to a fat point. It's the point plus its infinitesimally small neighborhood, its tangent space, first-order continuous structure, all encoded in the algebra.
Just like Galois symmetry revealed the hidden integer structure inside irrational numbers, the nilpotent element 0 reveals the hidden continuous dynamic structure, the derivative, inside discrete algebra.
Beautifully put. The circle, as the symbol for 0 and the concept of 0 itself, included these nilpotent extensions, seems to be the central actor in bridging the discrete world of arithmetic and the continuous world of calculus and geometry, absence creating structure.
Okay, we have journeyed from simple dots on a circle, so Fibonacci numbers, prime number chaos, the core of AI attention mechanisms, and the philosophy of 0, all held together by harmonic symmetry from the circle.
It suggests a singular underlying mathematical reality connecting these domains.
And that brings us to the grandest unification project in modern mathematics, the Langlands program.
Indeed. The Langlands program, or Langlands correspondence, is often called the mathematical Rosetta Stone. It's a vast web of theorems and conjectures that propose deep, unexpected links between seemingly completely different areas of mathematics.
Specifically, it aims to unify.
Broadly speaking, it connects arithmetic objects, like Galois representations dealing with number fields and their symmetries, with analytic objects, like automorphic forms and L functions, dealing with analysis, harmonics, and complex functions, and geometric objects, like algebraic varieties, curves, defined by polynomial equations.
Arithmetic, analysis, geometry. The 3 pillars. How does our simple circle problem fit into this framework? Is it just a trivial example?
Far from trivial. Our cyclotomic field math BBQzaton is one of the most fundamental entry points into the entire Langlands program. It sits at the intersection of 3 domains. Math BBQs and its Galois group represent the arithmetic side. The Fourier analysis on the circle, the cosines, the Chebyshev polynomials, that's the analytic side, connected to L functions associated with the field. And the whole thing started with the geometry of point-satisfying 6 summand 1 equaling $1 implicitly for Senon on the circled area.
The circle through the cyclotomic field is a central node, a bridge connecting all 3 core areas targeted by Langlands.
It's a perfect concrete example where all 3 meet. This gives enormous weight to the idea that the structures we've analyzed, the integer coefficients, the global invariants, the connection to Chebyshev polynomials, aren't just mathematical curiosities. They are reflections of these deep, foundational Langlands correspondences.
Are there other related grand ideas that frame this?
Absolutely. We can bring in Grothendieck's theory of motives. This is more abstract. Motives are conceived as hypothetical, pure mathematical objects, like the underlying Platonic essences or the DNA of algebraic varieties.
The DNA.
The idea is that properties like the number of points on a curve over finite fields or the periods of integrals associated with it should all be encoded in its motive. Our integer polynomial function, its roots and coefficients are conjectured to be deeply related to the motive of the Fermat curve, 6 talents plus yn equals any 3.
The integers we found are echoes of this fundamental mathematical DNA.
That's the conjecture. And if motives are the fundamental building blocks, you'd expect the same motifs to appear across different mathematical categories.
Sounds like duality.
Exactly. This leads to profound dualities, conjectured and sometimes proven in modern math, like homological mirror symmetry. This proposes a surprising equivalence between categories of geometric objects, geometry related to physics, and categories of algebraic objects, algebraic varieties.
Different mathematical universes mirroring.
Right. And our relatively simple cyclotomic constructions, the interplay between the geometry of the circle and the algebra of the field, can be seen as basic, beautiful examples showcasing the kind of structures in these deep dualities.
And how does that fit?
Schultz's work represents a major breakthrough in building bridges between arithmetic over fields with different characteristics, like the rational numbers, characteristic 0, and finite fields, math BVFEO. Characteristic Kyle. Perfectoid spaces provide a unified framework, a common language, where you can understand the properties of something like our circle system simultaneously across vastly different number systems. The trigonometry over real numbers, arithmetic and rational numbers, and the algebraic structure over finite fields can all be seen as facets of one single coherent object.
It provides the grammar to translate between these worlds, confirming they are aspects of the same thing.
Yes. It makes the Langlands type correspondences more concrete and computable.
The deepest lesson here, then, consistently reinforced by the sources, seems to be that mathematics really isn't an invention. We're not making this stuff up.
It feels like discovery.
The fact that the very same cyclotomic structures, the same symmetries, the same polynomials, appear in Gauss's work on constructing regular polygons in the 1800s, in Andrew Wiles's proof of Fermat's last theorem in the 1990s, and now in the attention mechanisms of GPT-4.
It proves these core organizing principles of arithmetic, rooted in the circle, are universal. They are inherent in the structure of reality, or at least in the structure of logic and quantity itself. Hashtag Doug Outro.
Wow. What a journey. Seriously, 7 elementary dots on a circle and looking at the cosine function? Yeah. It ended up being the blueprint for computational intelligence.
The circle doesn't just sing a mathematical song. It orchestrates intelligence by providing stable, harmonic structures for complex computation like attention.
The key insight for understanding where AI is going is that the most powerful systems seem to tap into, discover, and exploit these deep, inherent number-theoretic structures.
It feels like success comes from aligning computation with the underlying arithmetic grammar of the universe, the structures that have always been there.
Let's make sure everyone walks away with 3 crystal-clear takeaways from this deep dive. What's takeaway number 1?
First, for mathematics, symmetry is profoundly generative, not just restrictive or aesthetic. We saw through Galois theory how the perfect algebraic balance of the cyclotomic field makes integers inevitable, even creating them out of apparent irrational chaos. Symmetry builds structure.
Symmetry creates. Takeaway number 2. For AI.
Second, in computation and AI, all sophisticated learning, the kind in transformers with attention, context, positional encoding, is fundamentally harmonic learning. It relies on the stable orthogonal basis provided by the circle's geometry. Tools like sines, cosines, and crucially, Chebyshev polynomials are essential for ensuring spectral fidelity and preventing information loss.
Harmonic learning. The third takeaway. More philosophical.
Sometimes the zero, the absence, the thing that isn't there, is the main character. Think of the excluded root $6 in our polynomial, which enabled the structure of Fior Ekist, or the nilpotent element squaring to 0 but carrying the derivative. Absence, nullity, the void, it often creates the essential structure, stability, and integrity of the system. Don't underestimate the power of 0.
Symmetry creates learning as harmonic, absence structures, powerful stuff. Are we really teaching machines to think in some novel way, or just getting really good at teaching them to recognize and use the eternal, elegant mathematical song the circle's been singing all along?
Are we translating the fundamental grammar of reality for them, the grammar based on harmonic symmetries? Something to ponder.
Definitely. And we want to encourage you, our listener, to join in this exploration. Try to find your own examples of this principle.
Look around. Any physical system, computational process, biological pattern where some underlying symmetry seems to force a clean, rational, or ordered result despite messy or seemingly irrational components.
If you find one, share it. Tag your discoveries on social media using hashtag #CircleThatThings.
We'll gather them up and maybe roll through some listener findings in a future segment. It'd be great to see what you find.
Absolutely. Thank you for joining us for this ambitious return episode. We hope you enjoyed the deep dive.
We'll be back soon, diving into our next batch of fascinating sources. The harmonic polytope. Sounds intriguing.
Until then, keep thinking.
Until next time.